Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 17.5. In this section, we're going to be learning how to compute the Laplace of integrals. Yes, you can actually compute the Laplace of integral functions. Let me show you what that looks like. So we can compute the Laplace of the integral from 0 to t of f of x dx. Okay. So to compute the Laplace of an integral function, this is equal to 1 over s of the Laplace function. Literally. In other words, this is f of s over s. Right? You're probably mind blown. This is too good to be true. This answer is too clean to be true. But it is actually true. It is indeed true, and I can actually prove it to you. Right? If we were to have an integral from 0 to infinity of e to the negative st, and then our ft is from 0 to t f of x dx, okay, and of course dt. All right, so we pretty much have this. We have an integral inside of an integral, right? But what you can do with integral functions is you can derive it, right? Apply the fundamental theorem of calculus. So how do we do that? Integration by parts. And then we integrate e to the negative st. Right? Now this is simply negative f of t, and this is negative what? 1 over I'm sorry. We are deriving by t, so our constant is s. So we would have 1 over s e to the negative st. I just had to double check. I had to double check on that. Okay. So now what we have here is now we have the negative 1 over s e to the negative st of integral from 0 to t f of x dx from 0 to infinity. Now, of course, when we plug in infinity, right, our s is going to become 0, so this whole portion is going to be equal to 0, right? And then if we plug in 0, this t equals 0 is going to make this integral 0, so this is also going to be 0. Okay, so this whole portion is going to equal to 0. Okay, and so now what we're left off is we have from 0 to infinity, we have e to the negative st of f of t over s. Oh, what is this? This is simply the same thing as 1 over s of the Laplace of f of t, which is equal to f of s over s. Okay? And there you go. How beautiful. So so the Laplace of any integral function is equal to the Laplace of that function over s. Okay? So now let's go ahead and apply this. Alright, now we're starting to getting a little introduced into some special functions here. So what is this? What on earth is si of x? So what that is, I guess I could just put it in Laplace transform. Si of x is equal to from 0 to x of sine t over t dt. So that's literally what our Laplace is. Alright, so how do we compute this? Easy. This is just simply 1 over s of the Laplace of sine of t. Right? I'm sorry, no. This whole integral function. So 1 over s, we are Laplacing sine of t over t. There you go. And if you remember from our previous videos, right, the Laplace of sine of t over t is inverse cotangent of s. And our s for here was equal to 1, right? So our answer, inverse cotangent of 1 is pi over 4. So our answer is simply pi over 4. Okay? Just for that integral. Alright, let's go ahead and do another example. Okay, we have another special function. What on earth is EI of x? Or what is EI in general? So EI is the exponential integral. So to turn this into an integral form, this is simply, this is technically negative from t to infinity. Or let me put x. I use x. There we go. And this is e to the negative t over t dt. Okay. So how do we compute this? This is the same thing like usual. 1 over s. This is the Laplace of e to the negative t over t. I forgot to put a negative. I almost forgot to put a negative. Don't forget this negative. That could have killed all of us. So now s is equal to 1. Right? So our answer is just simply negative ln of 2. Okay? If you remember, what we had before is we had pretty much, you just want to find the Laplace of e to the I negative x again, right? Or, yeah, pretty much you just want to find this again. However, now that we have x at the front, we want to differentiate, pretty much. So this is, we want to differentiate. So in other words, the Laplace, if you remember, the Laplace of e to the I negative x, or pretty much from our last integral, the last example that we did, we had ln of s plus 1 over s. Well, it was negative. If we derive, so because we have the x at the, we have x at the front, we do the differentiation. So it's negative derivative of negative ln of s plus 1 over s. Thankfully, the negative cancels out, so that's going to be okay. So what we have is, this is, if we do quotient rule, right, we have what? S plus 1 minus ln of s plus 1. This is all s equal to 1. Okay? Let s equal to 1, plug it in, and you can see that our answer is simply 1/2 minus ln of 2. Okay? That's it. So very tricky, just be very, very careful. I think e to the I is the most difficult because of this negative to keep track. And the reason why we have negative x is, if this was positive, then this whole integral would diverge. So that's why that negative exists there, just to make this integral convergent. How on earth are we going to apply Laplace transform on this? So for those who don't know the ERF function, I can go ahead and kind of rewrite it for you. So the ERF function, x e to the negative x squared, and I'm going to go ahead and write the ERF function for you. The ERF function is defined as 2 over root pi from 0 to x, and then e to the negative t squared dt. Right? It's like a reverse Gaussian integral, or pretty much like making the Gaussian integral equal to 1 with this constant. Right? So let me go ahead and put this, close it with this integral. Here, I'm going to rearrange this integral a little bit. So I'm going to move everything to the side. Okay, I'm going to move everything to the side, so we have like 2x e to the negative x squared over pi, root pi. Okay, and what I'm going to do over here, I should probably color this yellow. Okay, so here I'm going to do kind of a u substitution pretty much. So I'm going to let u equal t squared. And so what's going to happen is I get from 0 to x squared e to the negative u over 2 root u du dx. Okay? And now I have from 0 to infinity. So once I simplify this, I'm going to also perform a u substitution here as well. So let's consider like w, let w equal x squared. Okay? So now what I'm going to get, I'm going to take the 2x with the substitution, of course. So we're going to be left off with e to the negative w. Okay? And then we have 2 root pi. This outside portion here controls everything here, including this inside. So because I let w equal x squared, this portion here is also w. Okay, so be very careful. Be very. Oh, I'm sorry. The 2 is this is the 2 that came from. So we just have this. Okay. du dw. I know it's a little tricky, but this is now a Laplace integral. So following with this, e to the negative w, so s is equal to 1. So we have the Laplace of 0 to x of e to the negative x over square root of x. Oops, I'm sorry. I should probably not do that. Use a different variable. dt. Okay. And s equals to 1. Okay. So, now what? Well, I mean, because s is equal to 1, 1 over s is going to be 1. So if you think about it, this is the same thing as 1 over 2 root pi Laplace of e to the negative t over root t. Okay? Now, you're probably thinking, I don't know this Laplace, right? Remember, I'm going to color this green. Remember this, the linearity? Whenever you have this is equal to f of s minus a. Okay? So what we have here, technically, is this is 1 over root 2 pi. Okay? This is, what's 1 over root t was pi over s minus a, but our a is what? Negative 1, so this would be pi over s plus 1. Okay? Of course, s is equal to 1, so now our answer is going to be 1 over 2 root pi. This is going to be square root of pi over 2, right? So our answer, our square root of pi's cancels out. So our answer is 1 over 2 root 2. And this is our answer. Okay? Alright. That one's a tricky one. This last integral, this last example is a very tricky one. So definitely practice this one to get around and just kind of maneuver, because this was a lot of manipulation, right? I bet you never expected this integral to be a Laplace transform integral, but it is, secretly. I think there's other different methods that you could go about this as well. Probably integration by parts, where you let u equal earth, I think. I don't know if that helps. So that's about it. I hope that was very helpful. And yeah, thank you so much for watching. I'll see you guys in the next part.